Hello, I'm Mike McCulloch. Today I'd like to talk to you about the Hubble tension, which is something of a big issue in astrophysics at the moment. So the problem is that astronomers have used Planck satellite data to measure small variations in the cosmic microwave background that existed in the far distant past, and they've used that to tune the lambda CDM, the standard model of cosmology, and they've run that forwards to predict the situation of the cosmos today. And what they get is that the Hubble constant today should be 67 kilometers per second per megaparsec. So that means at a distance of 1 megaparsec from us, the stars and galaxies should be moving away from us at 67 kilometers per second, and that recession velocity increases as you go further away. So far so good. Then they have tested the model by looking at what the actual acceleration is. So they've measured that using stars, galaxies and supernovae that are actually closer to us, so local if you like, but still millions of miles away. And they've worked out how fast those are accelerating away, and they've found that they're accelerating more, 73 kilometers per second per megaparsec. So this has given them a headache, so they've called it the Hubble tension. But I tend to think of it more like an actual disagreement. So what is the actual difference between these two numbers? So difference between 67 and 73 kilometers per second per megaparsec is about 6,000 meters per second per megaparsec. So if you extrapolated that to what the speed would be at the edge of the observable universe, you get about 10 to the 8 meters per second. And then if you work out what acceleration you need to get you to that speed in the supposed age of the universe, then you get 2 times 10 to the minus 10 meters per second, which those of you who follow quantized inertia should recognize instantly as being the minimum acceleration predicted by quantized inertia. So the obvious suggestion at this point is that they have simply missed out quantized inertia from the model they use to extrapolate from the cosmic microwave background forwards. And if you put quantized inertia back in there, you get this extra acceleration, which makes it all fit. So this is nice and elegant. So it's not perfectly clear whether how this all fits together yet, in that I dislike the idea anyway of the actual universe accelerating away from itself, because it requires an awful lot of energy, dark energy. I think probably something else is happening, and quantized inertia may predict a kind of more like a steady state for the cosmos, but I'll deal with that another time. Okay, so I hope you've enjoyed this short, and I look forward to talking to you next time. Goodbye.